Welcome back to the video lecture series for Introduction to Additive Programming using Scala. In the last video, we started talking about graphs. We said that we're going to work with recursion, and we drew a little graph. This graph has 4 vertices, 0, 1, 2, and 3. As is customary, we number them off and start at 0. Other applications you might want to give them names or whatnot, but this works fine for us. And the graph has these vertices as well as edges that connect the vertices. And we said the edges can be directed, as they are here with little arrows. For some things they wouldn't be. They can also have values attached to them, what are often referred to as weights, though what exactly they mean differs by application. It turns out that for students who have worked through the textbook, one of the projects from the first half of the book, the first semester worth of material, was a project to write a text-based game, and you would have the ability to walk from one room to another by going through various exits. That problem basically was a graph, and if you have extended on that in the second half of the book using with the project for a MUD, you're also writing a graph as a representation for the map. We're not going to be doing this for our text-based map, so that there are some projects that you can do there. What we want to talk about in this video is how we can represent this inside of a Scala program. So if we bring up Eclipse inside of the ADT package that we already have, I'm going to go ahead and I'm going to create a new, I'll just create an object for now, and I'll call it graph. Representing general purpose graphs is fairly hard to do, so that is actually a problem that I'm not going to try to write a general ADT for the graph. I'm going to hard code this more, and that won't be a significant issue for us here. So we have this object for a graph. How can we actually represent what is in this picture inside of our code? There are 2 basic ways that we represent graphs inside of code. One, the way which is kind of more object-oriented, is that we have a type for our vertices. So we could have a class called vertex, and inside of each vertex we would need to have some type of sequence of edges coming out of it. And each edge, if this were a directed graph, we definitely want to know the vertex that it connects to. How about we call it the destination is a vertex. Actually, they were vowels. I need to put them up in here. We'll see whether or not we can do this. Because you can have cycles, some of these things are probably going to have to be vars, or we'll have to have the ability to add things in later. That could happen inside of the vertex. And for now, I'll go with a val. And in fact, heck, why don't we just go ahead and make our edge a case class, because it's simply going to store data for us. We'll go with a weight as an int, and that's a happy edge case class for us. And then the vertex itself stores whatever data is supposed to be associated with the vertex and a sequence of edges. So I'm going to go with a buffer in this case. So we'll call it edges is going to be a mutable buffer of edge. We'll start it off empty and just go with equals import collection.mutable. and this will be happy. So this is one way that we can represent it. This is actually the data representation that is used, for example, in the text adventure or the MUD, where your vertex is a room, and the room has exits coming out of it, and so each one of these, you have a list, buffer, array, however you wish to represent it, of exits from a room. In addition to just having these edges, your room had things like a description and a name and stuff like that. But this object-oriented approach, where we actually have classes for our vertices and edges, is very helpful for certain types of graphs. However, it's often much more efficient to use a more compact representation, and I'll come back in the next video and we'll talk about what's called an adjacency matrix, and we'll see how that can be used as a more compact version of representing graphs.